All right, this is the second of perhaps a two-part series of lectures dealing with what I call simple circuits. Let me show you a diagram once again of a simple circuit, this time introducing a new element to our circuit. You may recall the symbol for a battery. A battery can be referred to as an agent that provides electromotive force. As I said before, it's a misnomer. The electromotive force is not a force. In fact, what it is a measure of how much energy the battery uses for every coulomb of charge that leaves the battery. The units of electromotive force, as I showed you last time, are not joules per coulomb, which would be legitimate, energy per coulomb or energy per charge, but is instead taken to be a volt, and one speaks of indeed the voltage of a battery, synonymously with the expression the EMF of a battery, the electromotive force of a battery. I show current symbolized as I, leaving the positive terminal of our battery and circulating around the circuit, appropriately named circuit for circulation. On its way back to the negative terminal of the battery, the current passes through some object. It could be a light bulb. Anything in a circuit that gets in the way of the flow of current, that has current pass through it, is called a resistor because it inhibits or restricts the flow of current. The symbol for a resistor is R. The symbol in a diagram of a circuit, the symbol for a resistor is that sawtooth symbol. You'll recall the straight lines are just the connecting wires in this circuit. The units of resistance are ohms, named after George Ohm. The symbol for it is a Greek letter, uppercase omega. So R symbolizes this property of resistors called resistance, and R is also the symbol used to designate the thing that has that resistance. Well, last time I indicated to you, I would tell you how one could know what the current is that comes out of a battery and circulates around a circuit. Well, there are devices called ohm meters, ampere meters, that can be used in an appropriate way to measure the flow of current out of a battery. Alternatively, you could use an equation based on a law, Ohm's law. Ohm's law applies only to a circuit of this type called a simple circuit. A simple circuit, I'll declare now, finally, is a circuit in which there's just one battery and one resistor, and we don't count the connecting wires. For a simple circuit, Ohm's law applies. You may calculate the current that comes out of the battery by dividing the voltage of the battery, the EMF of the battery, by the resistance in the circuit. Let's work a sample problem. The EMF of our battery is 60 volts. The resistor has a resistance of 10 ohms. The current out of the battery, according to the E over R equation, is 60 volts divided by 10 ohms. I'm dropping the units. As long as we're using standard units in this ratio, and we are, then the final result for the current that we're going to calculate will be standard units, amperes. And so we have 6 amperes is a current out of the battery, and we speak of it as being the current in this circuit. Current has nowhere else to go but to circulate around and around and around. Well, an ampere is a coulomb per second. So another way to describe the current out of this battery is that it is 6 coulombs with each passing second. Let's ask the question, how many coulombs, or how much charge, we could say, leaves the battery in, pick a number, what, 30 seconds? Fine, I'll pick 30 seconds. How much charge leaves in 30 seconds? Well, 6 coulombs needed for each second. And so we have 6 times 30, or 180 coulombs. And I've used an equation that you really don't need. Common sense tells you how to calculate the charge. If you are outputting 6 of them, 6 coulombs each second, and you do it for 30 seconds, well, of course, it's 180 coulombs. So far, so good. The next thing I'd like to calculate is how much battery energy was expended. This is probably chemical energy that's used to push the charge around the circuit. You'll recall that the energy that is used to push 1 coulomb of charge out of the battery is just whatever the voltage of the battery is. Or you could take the voltage of the battery, in this case measured in joules per coulomb, 60 volts, you might recall, probably don't. A volt is a joule per coulomb, so we have 60 joules per coulomb here. It means that for each coulomb of charge that leaves the battery, 60 joules of energy is consumed to make that happen. Well, we have 60 joules per coulomb, and we have 180 coulombs multiplied. This is how much energy was consumed during 30 seconds of operation of the battery of the circuit described here. We won't stop there. Let's calculate now what we can call the power output of the battery. Now, the power output of any agent, whether it's an animal, a human, a machine, in this case a battery, is the amount of energy that it expends or creates per second. Energy measured in joules, time measured in seconds. And so we can calculate the power output by dividing the energy that was provided to the circuit, energy provided divided by the time it took to provide it, 10,800 divided by 30 seconds, and the units will be joules per second, and there are 360 of them. Now, maybe you even recall that a joule per second from the old days is a watt, a power unit. Final result is that the power output of our battery is 360 watts. Now, you don't have to think of the power calculation in this step-by-step method. I'm going to give to you a simple equation that you can use to more quickly get the power output of a battery, but be warned, the power output of a battery equation I'm soon going to show you is only valid for what kind of circuit, he asked? That's right, a simple circuit with 1 battery, 1 resistor. All right, the equation I'm referring to is what people like to call the pi equation. P for power, I for current, and script E for the EMF. There's your P equals IE equation. I'll leave it for you to confirm that you can get the 360 watt answer by multiplying I, which is the current, which is 6, times the voltage of the battery, which is 6T. 6 times 60, you'll have to take my word for this, 360 watts. Final answer. This concludes the second of our series of video lectures on simple circuits. Soon we'll talk about more complicated circuits, maybe even in the next video lecture. I hope this will help you.